Some of the most interesting places in the solar system are really far away from Earth. And so if you want to be able to get out there, you need to be able to go fast, or unless you're willing to wait decades to be able to arrive at your destination. And so scientists are thinking about methods of faster propulsion. And one of the most exciting ideas is electric propulsion. Now, you're familiar with ion engines, of course, but these come in different flavors where you can accelerate particles out of the back of a spacecraft using an electric field, and you can get enormous velocities, tens, maybe even hundreds of kilometers per second in delta V. Enough velocity to get out to the solar gravitational lens. My guest today is Dr. Dan Fraser. He is an assistant professor of aerospace engineering at the University of Kentucky, and he's part of a group of researchers who wrote a recent paper about looking at how different kinds of electric propulsion systems could get us out to the outer reaches of the solar system in dramatically faster times. They calculated that you could reach the solar gravitational lens at 550 astronomical units from the sun within about 13 years, which is pretty fast. So enjoy this conversation with Dr. Dan Fraser. Dan, we talk a lot about ion engines here on the channel, but for people who are unfamiliar with what an electric propulsion system is, I think because we're going to spend so much time talking about it, can you give a description of what they are and how they work?
Yeah, I would say on the lowest level, what it really means is that you're exploiting the fact that charged particles react to electric and magnetic fields. And so that way you can impart momentum, you can impart energy onto the charged particles just by imposing certain types of electromagnetic fields. And it's a very efficient energy conversion process, an energy transfer process. And that's really what electric propulsion systems are based on.
And I mean, we've seen that you have like some cloud of xenon or krypton, and then you are accelerating them out the back of the spacecraft with a electric field at tremendous velocities. What sort of applications do the ion engines, are they more effective than a more traditional chemical rocket that we're also familiar with?
Yeah, so the type of engine you're describing is actually sounds like an electrostatic type of electric propulsion systems. There are actually other types of electric propulsion systems, and we can talk about that a little bit more. We can stick with the electrostatic for now.
No. I mean, the one that you're, because we're going to get into your research and what you're proposing. Yeah. So if you want to describe a different flavor of this, I think that's all perfect.
Yeah, I mean, there's three main types that are usually being considered. One is the electrothermal type of propulsions, like a resistor jet, where you use the dissipation of electric energy as heat in a medium to heat it up and then to expand it. So that's very reminiscent of a classical chemical system, except you're not using the internal energy of the fuel, you're externally adding energy. Then you have things like the electrostatic propulsion systems, where you have a potential difference between 2 points, and you're accelerating a charged particle along that. And then you have the plasma dynamic propulsion systems, where you generate a plasma and then you use magnetic fields to accelerate and compress the gas and impart additional energy that way.
So. I mean, what are the strengths of these different ideas? Which, where do they work well?
Yeah, so resistor jets, they're very simple in a way. They're relatively simple to integrate. You can make them very, very small. There's currently a push to miniaturize electric propulsion systems. Same ideas with CubeSats to democratize space access, democratize access to these high-performance propulsion systems. So resistor jets are very good for that. For electrostatic systems, the big advantage, I think this goes back to the original questions you asked, is this more efficient than a chemical propulsion systems or something else? And it is more, it can be more efficient, but the key is that it covers a different niche. So chemical propulsion systems usually are used to generate relatively high thrust, right? So that is the mass flow times the speed of your gas particles, of your gas volumes. So with a chemical engine, you can get a very high mass flow rate, but the maximum speed of these gas particles that make up your exhaust is limited by the internal energy content of the fuel. In the case of an electrostatic system, you're only limited by how big of a potential you can apply. So you can imagine that you can get to much higher velocities, right? And we're talking kilometers, tens of kilometers per second, which is significant. The trade-off is that in electric propulsion systems, you often work with very small mass flow rates. So you have very high velocities, very small mass flow rates. Your thrust is very small, but your specific impulse is very high. And so if you're already in space where you don't have to overcome the gravitational potential of a planet or some other body, this specific impulse is really what allows you to go to far away places faster. And that's where the big advantage of these electric propulsion systems comes in.
Right. Like if it was drag racing, the chemical rocket is going to beat the electric propulsion system off the line, but
yes.
See how much fuel you've got a year later. The electric propulsion system is still going and going while the chemical rocket ran out of power, ran out of juice,
Exactly.
Within the first 3 minutes.
Exactly. Yeah.
Yeah. But so this idea of the plasma electric propulsion system, like I don't think my audience is very familiar with this idea. Mm-hmm. Where does this have its benefits compared to the ones that maybe we're more familiar with?
Oh, yeah. So if you take like some examples for electrostatic ones, I'm just making the comparison. So there's like the Hall thruster, the gridded iron thruster, and they often work with xenon, krypton. Recently, there's been progress to do it with iodine. And that works all great. But really, you're limited to these elements, right? So, and relatively low mass flow rates, like I said. So you cannot amp up the thrust there. So if you need thrust, for example, to lift up the ISS so it doesn't crash into the atmosphere, it's going to be very difficult to do that with a Hall thruster. If you go to something like a plasma dynamic system, especially the ones that are inductively coupled, you're not limited to these type of elements. Really, you just need some gas that you can ionize. And at low enough pressures, you just need to achieve breakdown to get an initial plasma going. And then you'll have something, for example, a radio frequency generator, a radio frequency plasma generator. So you have a magnetic coil that creates an RF magnetic field. That RF magnetic field drives a ring current inside of your ionized gas. And this ring current is what keeps the plasma production going and which energizes the plasma. So then you have this really high enthalpy gas flow. And we're talking, if you let it expand into equilibrium, we're talking about thousands of Kelvin. So this really high enthalpy gas flow that is partially ionized. And so now we can actually then add an electrostatic system on top of that, or another magnetic system, then that would be called a magnetic nozzle, to accelerate, to further energize the plasma, to not only get high specific impulse, but also to get relatively high thrust. Right? And when I say relatively high thrust, I'm saying newtons, tens of newtons, hundreds of newtons. Still not in the realm of chemical propulsion, but way above the millinewtons that we're used to from something like a Hall thruster system.
Right. So it's kind of like a 1-2 punch, right? That you get that raw thrust coming from the plasma itself, which already, if you just took a gas, energized it, fired it out the back of your spacecraft, that would give you a certain amount of thrust. But then you are also using the fact that it's ionized to add even more velocity to that propellant using electricity.
Yeah, because you can couple it to an external electric field. You can energize it. You can manipulate the trajectory of the gas. Right, so you're really starting to exploit the fact that here is a gas that is susceptible to electromagnetic fields, and you can control electromagnetic fields. We're like actually pretty decent at constructing electromagnetic fields, certain topologies of electromagnetic fields with specific properties. And so this is really where you can leverage these plasma properties. And this is also like where it goes into the engineering realm, right? We're going away from pure basic plasma physics. We're talking about, well, now we can combine kind of fluid mechanics, plasma physics, and electromagnetics, put them all together and build these completely new is a little bit of a stretch. I always say we've done everything in the 60s. Now we're just repeating it.
Right. Yes.
But,
I'm sure there's some old NASA papers that are describing exactly what you're proposing. And,
or from the Soviet Union, probably. I mean, those guys were the pioneers in this area. You're coming up with this new system that really allows us to turn more knobs to control better what is happening, and where we're not so limited by the intrinsic properties of the fuel, and we're not limited to these very specific like noble gases. We could put the dirtiest stuff that you can imagine in there. As long as you can gasify it and you can ionize it, you're fine. Okay, so in a Hall thruster, you're a little bit more limited because the plasma is actually in touch with the electrodes. You need this relatively low ionization potential. You don't want to lose energy to dissociation. Well, you don't want to lose that in the other case either, but it's not quite as important. But
right.
Yeah.
I like that idea that you could put the dirtiest fuel. I could just sort of imagine just shoveling hydrogen, water, rock, whatever, heat it up, turn it into a plasma. You're good to go.
Yeah, exactly. Yeah, you could even like waste product from astronauts. In principle, you could use for something like that. Yeah.
Oh, that's really interesting. Okay, so we've got this propulsion system, and so the paper that we're talking about today was you and your colleagues looked at what is the kinds of missions that could be done with this kind of a propulsion system, and you explored 3 different missions.
I want to add there that in that paper, we are not just talking about the propulsion systems that I just talked about, but there we were also considering laser electric propulsion, which is a very promising and interesting system. And there's also the idea to use solar electric, right? So I think you mentioned it in the beginning, yeah.
Right. So let's talk about the laser electric, and then we'll talk about the solar electric. So how does the laser electric work?
Yeah. So essentially, the laser electric is kind of a specialized form, I guess, of solar electric, where you beam energy to the spacecraft in the form of a laser, convert it to electrical power, and then use that to couple into your electric propulsion system. Right? So in the end, again, you then will have a grid thruster, you'll have a Hall thruster or something like that. But what that allows you to do is it allows you to massively increase the energy density of the system that you're using. Because if you're using solar electric, you're limited by the area of your solar panels. You're limited by the solar constant, depending on where exactly you are. With a laser system, you profit of the fact that you are only limited by the energy density in this laser beam itself.
So you don't have to carry around the weight of the solar panels. You just have to carry around the ability to catch a laser that's pointed at your spacecraft without that laser burning a hole in your spacecraft. Like it's a tricky balance. Right, right. And there will be a regime. Like in some cases, if you're close to the sun, then solar collection makes a ton of sense. And if you're far away from the sun, then laser collection starts to make sense. And I guess it depends on the infrastructure. If you have laser arrays positioned at Jupiter, for example, when your spacecraft is coming to do its gravitational assist past Jupiter, it also gets a boost from the local laser, right? So
yeah, you could think almost of like a highway system, right? In principle, if you build up an architecture like that, it would allow you to have electric spacecraft with significantly higher accelerations than what would normally be possible. And so you could really shorten the trip times between these different stops in the solar system.
Yeah. It really feels to me like that infrastructure will give us the sort of, that's how we know we're starting to turn into a true spacefaring civilization. Once we've started to deploy that infrastructure and we're like, which of the routes do I want to take? Oh, we know there's an operational laser over Jupiter, so we'll take the Jupiter gravitational assist. as opposed to the the Mars Lagrange point one, whatever, right? Like that there are these options and stuff, and you can see it gets easier and easier to then explore the rest of the solar system once you've got this stuff deployed. Okay, so then let's talk about again the the kinds of missions. You guys had proposed a mission to Jupiter, a mission to Pluto, and then most excitingly a mission out to the solar gravitational lens. So take us through those scenarios.
I mean, what those missions have in common is that you need a lot of delta V for them, meaning you need a lot of energy to get there. And it's difficult to do them with chemical propulsion because of the Tsiolkovsky equation. So you just end up with a massive spacecraft that is 99.999999% propellant. Right, and you somehow have to lift all of that into orbit, and you have to launch it, and your payload in the end is tiny. Right, so the idea here was, well, we have these electric propulsion systems, and we know that in principle they provide us this advantage of a much larger specific impulse. So let's see how far can we push this. And this is also kind of the organization in which I'm a volunteer in. The Initiative for Interstellar Studies, like the name suggests, the goal is to enable interstellar exploration, meaning beyond the heliopause. Right. So Pluto is well within the heliopause, but it's very far away. So there, the idea is, can we get there faster to do more science? Can we expand our sphere of influence? And then the mission, of course, to the solar gravitational lens. That is really where we're starting to get further out of our, let's say, realm of comfort, where we're really operating very far away from Earth, where it's difficult to get large payloads there, and see what is possible. And also, and I think this is important, if you read the paper, you see there's assumptions being made to enable some of these missions, like the power plant power density, the conversion efficiency of electric power to propulsive power, that are very optimistic. Right? And you could say, well, this just means it's complete nonsense. It doesn't exist yet. But that's exactly the point. The point is to show, well, if we can get here, we can do these very optimistic missions. And we can do these missions with a very high return value. And so there's an incentive for people to look at these specific problems. Like we have Hall thrusters, we have gridded iron thrusters. We are making them more efficient. What else is needed to enable these really far-reaching missions into places that we haven't been as much, where we could really learn a lot? Like, I mean, the mission to the solar gravitational lens, right? The idea is to use the gravitational lens of the sun as a massive telescope. It would expand our capabilities in a scientific sense enormously beyond anything that we're currently capable of.
Right. So then, even with those optimistic ideas, I'm assuming, first principles, you're not violating the laws of physics. So it's like, it's an engineering challenge, not a new physics challenge. So give us a sense, and let's do the exciting one. Let's talk about the solar gravitational lens. So give me a sense of how that mission would work.
Yeah. I mean, so we're talking about, that mission would work pretty much how any electric propulsion mission would work. We're talking about a delta V of about 190 kilometers per second. So that is an enormous amount of energy.
Yeah, it's a lot.
And that's because we want, in this particular setup in the paper, we have a travel time of 13 years. So that's actually
13, yeah.
13, 1-3, yeah. So that's actually very reasonable for a mission that goes out to 550 astronomical units. Right? So you're like, okay, so that's why there's so much energy needed. If you say, well, I'm fine with needing 30 years, you could do this with less delta V. Right? But so you have an electric propulsion system. So if you play Kerbal Space Program and you use the chemical propulsion system, you're familiar with having to do these point boosts to adjust your orbit, right? You need to get ideally in the perihelion. You do your little point boost with your propulsion system. You start expanding your orbit until you go parabolic or hyperbolic, and you switch orbits, right, to go into the next place.
I really appreciate you putting this in terms of Kerbal Space Program. I think that is that is like a language we can all understand.
Yeah, I think they do a great job at visualizing it, right? Because you can watch the ellipses of the orbit to grow, and at some point it's like, oh, I'm not bound anymore by the gravitational attraction of this body, right? So that's exactly what's happening. If you do it with an electrical spacecraft, you do not do these point adjustments. You would fire constantly, essentially. You would fire the propulsion system constantly, and you would do what's called spiraling up. So instead of doing this Hohmann-type transfer, where you go from one orbit into a different orbit, you're actually doing something that would look more like a spiraling up your orbit. And eventually, once you're in the near where you want to be, of course, then you have to make sure you go into a stable orbit there. But it's more of a constant, like you said earlier, it's more of a slow burn. It is not something that happens where you just fire the engine for a minute or two and you're done, and then you hope and pray that it's all worked out. You would constantly do this. You would constantly do adjustments of your trajectory, of the power on the propulsion systems until you get where you want to be. And that's kind of how the mission would play out on a basic level.
And like, what specific hardware would be operating? Like, would you, have you got a fusion reactor on board the spacecraft that is generating the electricity that is then, you've got astronaut waste, that you've collected and used just to prove that you can? No, like, what is give me a sense of like what's actually operating coast phase, burn phase,
So, it's a good point that you're bringing this up. So the power plant, power density. So power plant is the device that provides the electric power for the propulsion system. Is one of those assumptions. I would say yes. This is very optimistic for this paper, and I have to look up the exact number. So we're talking about in the paper. We're talking about 1,000 watt per kilogram, and this is 2 orders of magnitude above the current status for a nuclear electric propulsion system. Right. So,
nice.
Yes. So
right.
We are going into this direction where it would have to be something like a very efficient fusion reactor or something like a very efficient laser electric propulsion system where you get the energy remotely from a different point.
Right.
Yeah.
Or antimatter, like if you had a little bit of antimatter to sip away at for the journey.
If we do antimatter, we're not interested in electric propulsion anymore. I think then we do a direct matter antimatter annihilation reaction, and you have that's actually called a photon rocket. It's where you have perfect conversion of matter to energy, and then you just get photons out of that, and you use that for propulsion. Then we're not.
Right.
Then we would just skip the charged particles when we get to that.
Okay. All right. That sounds good. Yeah. Okay. So either you've got a type of fusion reactor that's incredibly efficient, where you've got this rate of energy, or you have very powerful lasers that are beaming the energy and it's able to grab it and use that for electricity. Like you're not going to get the power you need out of an RTG or a fission reactor. Like you really need something that is the next level technology. Yes. But
well, I don't want to say completely no, but I would say it would require a leap in capabilities. Yes, this is definitely one of the points in the paper. Is like, if you want to make it happen in this way, this is one of the areas where we would need to make massive progress to increase the specific power density. Yeah.
But if you're willing to be more patient, then you can scale down the power density. Like if you say,
yes,
fine,
absolutely,
we're okay with a 100-year mission out to the solar gravitational lens, then you can use something a little more off the shelf.
Yeah, exactly. Yeah.
Right. Okay. So we've got this spacecraft, it's launched, I'm assuming, on a chemical rocket. It's gone into orbit. Then it kicks on its whatever flavor of electric propulsion engine that you're talking about. It's making this spiral pathway around and around using its incredibly efficient system, and makes its way out to the solar gravitational lens, and you say in 13 years. Now, if I understand though, one of the issues with the solar gravitational lens is you want to kind of go down this very narrow cone to observe whatever is your target on the other side of the lens itself. So do you have to then change your spiral into a straight line that's moving away from the star at some point?
Yeah, I mean, you would still have to make these adjustments to reach the type of orbit that you're actually interested in. So at that point, it becomes, it's not unlike the chemical propulsion one, where you would, if you're on a parabolic or hyperbolic trajectory and you want to stay in this very specific spot, at some point you have to make an adjustment to reach that particular orbit, or that stay in this particular relative position. It's the same for the electric propulsion system. The difference would be that you start making the adjustment earlier, right? So instead of, like I said, an impulse adjustment here, one here, and then another one there, you do something for a long time, you fire for 5-6 years. It's like, okay, now we actually need to make sure we go into this orbit. So we start changing our thrust vector, and we start making these adjustments to make sure that we actually hit exactly that point that we're interested in. So mechanically, from an orbit mechanics standpoint, it's not so different with what exactly you have to do. It's just how you do it differs in timescales.
Right, I understand. Now, I let my patron membership know that I was going to be talking to you about this, and they had a couple of questions for you that are very related to where we are in the conversation so far. Alexander Gross asks, once a spacecraft has arrived at the solar gravitational lens focal point, would it be practical to move it along the 550 AU radius circle using electric propulsion to observe different targets? So I think, the downside of the solar gravitational lens is you get one target, and everyone's like, how do we get more? So do you think that you could efficiently continue on with that high thrust to go and be able to loiter at different targets with the lens?
Well, it's low thrust, high ISP. But in principle, you're limited by the availability of the propellant again, right? And how much are you willing to wait in between these adjustments? Now, I'm less familiar with how exactly the image formation, or how the image formation of the gravitational lens is limited, or what limits the targets exactly. But if it's just a matter of relative positioning to the sun, then in principle, you can keep using these propulsion systems to make adjustments in your relative orbit, as long as you have propellant.
Right.
So, yeah.
Always the problem, right?
Yes.
And Caradwin asks, what mass would a gravitational lens mission need, including its propellant? So even with that hyper efficient, 2 orders of magnitude more efficient fusion engine and its associated propellant.
Yeah.
How big of a spacecraft are we looking at here? What did you guys estimate?
We estimated about 45 tons. Yeah,
right.
45.
Okay.
45 ton spacecraft. Yeah.
So like 5 James Webbs packed together. Like it's a big spacecraft.
Yes, absolutely. I mean, this is like a flagship.
Yes.
Yes, it's a massive spacecraft to achieve this. And this assumes a payload of 18 tons. So, which is pretty significant if you compare missions to each other. So you can scale this down if you're willing to make the payload smaller. But that was one of the assumptions, and this is actually, so with this mission, this would be, I should have said this earlier. So what the paper does is it tries to optimize multiple things about the mission, right? So this is the approach, and one of the 2 most important things is, what is the ideal ISP for this particular mission? So then which electric propulsion system would fulfill that? Do we always need the maximum ISP to get the optimal payload fraction? Turns out no. It depends on the mission. There is an optimal ISP. And then what is the maximum payload mass fraction that we can get there? And in this particular mission and in this optimization process, the payload mass fraction was 40% for this spacecraft. And if you compare this to some other missions, this is actually an enormous payload fraction. Right? So if you're willing to move off of this optimum, then you can make the spacecraft smaller. But and of course, if the technology becomes fair, there's a lot of factors. But if you want to go for this optimum ISB, optimum payload mass fraction, then we said, well, then you're going to end up with this 45-ton, five James Webb Space Telescope spacecraft. Yeah.
Right. Yeah. A Star Destroyer that you're sending out
exactly.
Up to the solar gravitational
and we have to
lens.
build them at some point.
Yes. It's just a matter of time before we develop these. So then, obviously, you are part of the people thinking about how we actually get to other star systems. Do you think beyond getting out to interstellar space, beyond taking advantage of the solar gravitational lens and maybe sending a mission out to the Oort cloud or something, do you think that this technology route gets us to other stars, or is it still just insufficient?
As much as I would like to say it's enough, it probably isn't. There's some intermediate type missions. I don't know if you've heard of rogue planets.
Mm-hmm, sure.
Yeah, that's a very interesting topic. So free planets that are not bound to any star, that might be something we could achieve. Interceptor missions for interstellar objects might also be possible. That's definitely possible. But other star systems, there was this analysis done by a guy named Frisbee, I think like 20 years ago, a little bit more. And he tried to basically find the limits of different propulsion systems. And this is why Breakthrough Starshot, the organization that Stephen Hawking was supporting, why they decided to go with a laser sail for this interstellar mission, because in that study, he found the only reasonable propulsion system in terms of total mass, in terms of travel time. The only reasonable one is this remote energy system, this beamed energy system. You can probably do something with electric propulsion, or maybe, and then a lot of gravity assists. You can do something with chemical propulsion, a lot of gravity assists, but it will take you hundreds, thousands of years. I mean, hundreds is too low. It will take you thousands of years to get to another star system. So if there's no massive shift in the propulsion systems that we develop, then I think it's very optimistic to say that electric or chemical propulsion systems will get us to another star system within a reasonable time frame. I think, like I said, from this analysis, it had to be a remote beam system. An antimatter-matter system might be able to do it, because it's just so efficient. And then, of course, the holy grail of propellantless propulsion, but I'm not going to hold my breath for that until it's actually happening.
You mean the one where you actually do violate the laws of physics as we understand them?
As far as we understand them, yeah.
Yeah. We obey all of the laws of thermodynamics in this house. So
okay, excellent. Yeah, I mean, it's not impossible that we find some really fancy exception or some way to bend the rules, but at the moment, it doesn't look like it at the moment. People should work on it. I'm not saying they shouldn't work on it. I think it's very important to stretch the imagination, look for what's possible, but there's just nothing material there at the moment, I think.
I hope you enjoyed that conversation with Dr. Dan Fries. Now, we had a much larger conversation where we looked at his day job, which is focusing on plasma physics and what impact they have on hypersonic spacecraft. And so think about the heating from the plasma that we're all watching as the SpaceX Starship returns from space, and how the plasma is getting in and heating up the various control surfaces, the flaps, starting to burn through. What does plasma do to a spacecraft? How can you fly through the atmosphere for not just minutes, but maybe hours, and yet in a reusable fashion where you can come back again and again and fly? And what are the implications for the work that SpaceX is trying to do, figuring out how to make Starship survive its re-entry? Now, we put this conversation over on our Patreon channel. This is available to all members, both free and paid. So you don't have to pay us to be able to watch this additional content. You can get this over at patreon.com/universe today. And I'll put a link in the show notes directly to the additional bonus interview. Dan, what are you currently obsessed with?
I think my obsession at the moment is bringing plasmas into more engineering applications, like in aerospace engineering.
What are places that plasma ought to be? Because that seems, a little dangerous.
It's not dangerous when you do it right. I think things like there's plasma-assisted combustion, for example. So this is an active area of research where we can make combustion processes more efficient. We can control them better. We can have stable combustions at conditions where it would otherwise blow out. This would be a huge boon for anything that uses gas turbine technology. So energy production, current airplane propulsion systems, they would hugely benefit from this. Potentially also going into propulsion systems for scramjets. We mentioned very early the single stage to orbit planes, right? This is like systems where you have to operate over a wide range of very hostile conditions. And over conditions where normally you're not able to stabilize a combustion system. But by introducing either thermal energy through the plasma or radicals through this plasma decomposition process, we might be able to extend the stable operating envelope by a lot. Right? So that's one thing. Yeah.
Yeah, I love it. Like just, I guess for you, everything, your hammer is plasma and everything looks like a nail. Like at a certain point, you're like, how could ionized hot gas have, play a role here in this, blender, car engine, computer, who knows where plasma might find its way.
It's not just hot plasma. So you can, in the chip industry, this is very common already that you use cold plasmas where really the only thing hot are the free electrons. The heavy ions are very cold, almost room temperature, but the electrons are having tens of thousands of Kelvin temperature if you would try to measure it directly. And this non-equilibrium property of plasma is also something that potentially would allow us to tailor chemical processes, maybe even some fluid mechanic processes to exactly the way we need it, where we have not been able to exert active control before, and just rely on some sort of passive control. Which, of course, if you can do passive control, that's great. Then you don't have to do anything else. But if you get down to the nitty-gritty and you're working with processes that really need this really fine structured control, that is where we can introduce plasmas and control their properties, their spatial distribution, even their temporal behavior. Better. Yeah.
It's fascinating. Thank you so much for taking the time to chat with me today. I really appreciate it.
Yeah, my pleasure.
Now I'm going to talk about some other resources that we have here on the channel. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, Barry Lake Roofing, David Giltinan, David Matz, Dennis Liberty, Dustin Cable, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Roebuck, ScienceWorldRecord.org, SpiderSwap.io, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. So we talk quite a bit about the solar gravitational lens. And this is this idea that if you travel out to 550 astronomical units away from the sun, then the gravity of the sun turns into a natural telescope lens. And so if you then had a telescope that was only a meter across, but then you were using the solar gravitational lens to magnify, then you would be able to take images of exoplanets at just an incredible resolution. You could get a megapixel image of a planet orbiting around another star. The trick, of course, is to get out there. And so this interview is all about how could you get out there. But if you want to learn more about the solar gravitational lens, I've got an interview with Dr. Slava Turyshev. He is the originator of this idea of using the sun as a natural telescope lens. And I've actually got 2 interviews with Dr. Turyshev. One about the solar gravitational lens itself, and a second about some proposed propulsion systems with solar sails to be able to get out to that lens. So enjoy those additional interviews. All right, we'll see you next time.